So, we continue with our discussion on moving lines. So, we are simply analyzing one static cable, and today's class let us try to find out the moving stiffness, now which is very crucial to our calculations. And the other part that you will be required to know is the equations of motion. So, equations of motion are the vibration part. So, we will come gradually to this. So, this is our barge or your offshore structure. So, we are analyzing one simple line equation. So, your anchor line, let us say that this is making is a catenary, it is coming like this and it is lying on the seabed. So, this is your point of anchor. So, this is your H. So, this is how much? This is TH and this one is TW and this is phi W, and out here this will be, say at the seabed this will be T0. This is what we have. So, T0 has to balance your TH, then this is your water depth. Now, in this equation we have calculated the length of the line, if you remember. So, there are two values. Say if you take right up to the anchor point, say this is your anchor point, the whole length is this is your point of suspension of the chain cable to your anchor point, say let this be called this is L. And right to the point at which the line becomes horizontal, you call this as LS. So, this is your distance up to the point of suspension of the vessel. So, this is small x. Capital X is the distance right to the end of the line. So, this one you mention this as capital X. Now, today let us find the problem is find cable stiffness. So, we have already solved the static equation, static line equation, and we have derived the expression for TH, LS, length of the line and small h. So, these formulas have already been derived. If you look into your previous class notes, so you have derived this expression, that is LS square. LS, mind you, is the total is the length up to the where it becomes horizontal, the line. So, this is h square plus twice into HA. Now, please you do not talk. So, from this expression what is the value of LS? So, LS you can write as, so this is, if you take h square out, so this is 1 plus So, this will be how much? This is 2a over h to the power half. So, this is the expression for Ls. Alright. So, now what are the other equations that are required, and you have already found out the expression for the depth of water. Remember the expression that we have derived from z minus z naught. You look into your previous notes. From this we have found out, you tell me the expression for h. That is h we have put the z equal to 0 at the water surface. So, h is, if you look back into your notes, you will find this is a multiplied by cos hyperbolic of x by a minus 1. So, this is the expression we have derived from z minus z naught, and you put z equal to 0. So, from this you can find out what is now this x is the smaller x, that is this part of the length of the line. So, from here what expression we are getting? So, h by a you can take it outside. So, this is h by a plus 1. So, this is the expression for cos hyperbolic of x by a. So, from this we can get x by a. So, that is coming as cos hyperbolic inverse h by a plus 1, or 1 plus h by a. So, this expression we can derive. So, now you can write down the full expression for the length of the line. So, this is x is equals to a cos hyperbolic inverse 1 plus h over a. Alright. Now, one thing has to be remembered, that the value of a that we have assumed. What is this value of a? A is nothing but the horizontal tension divided by weight of chain, and this W is not the total weight of the chain, but chain per unit length, isn't it? What I have defined, the corrected for buoyancy. So, from here what is the value of TH we are getting? So, TH is A multiplied by W. So, what is our expression for capital X? The small x we have already derived as A cos hyperbolic 1 plus HA. So, capital X, if you look at the diagram, so what you will get? So, in this capital X is this distance plus small x. So, how much is this distance? From the horizontal portion. So, here actually if you take a tangent, this will be phi naught. This is your angle phi. So, now what is the equation for capital X? So, x is, how much is this distance? From anchor line, anchor point to the horizontal portion. So, this is capital L minus Ls plus small x. So, capital X is L minus Ls plus small x. So, now you write down the expression for capital X. So, capital L is the total length of the line, isn't it? So, that is remaining constant. Now, Ls is, we have already found out the expression for Ls. So, that is H multiplied by 1 plus 2A divided by H to the power half, and write down the expression for small x. Now, expression for small x is this one. So, this is A cos hyperbolic 1 plus H A. So, this is the total expression for x. Now, from this equation, say let us you put this as 1, you find out this dx over dA. So, what is this value? Now, A is of course constant, so this will be 0, but what about this expression? So, this expression will be this H is the depth of water, so that is also constant, you can keep it out, but A is a variable. So, this will be half. So, this will be divided by 2 multiplied by 1 plus 2AH to the power how much? Minus half. Any other term? Multiplied by 2 by H. And what about the next expression? So, next expression actually you have to do some simplification, otherwise if you want to differentiate the cos hyperbolic term, it will be too much of a headache. So, this is product of two functions. So, how much you keep first you find out dA by over A. So, that is 1 and keep the other part as constant. So, this will be plus cos hyperbolic inverse 1 plus HA. So, you are differentiated only with A multiplied by this. Now, you keep A and differentiate cos hyperbolic inverse with respect to A. So, what is the function? So, here what has been done? Some simplification has been done. Now, simplification is this cos hyperbolic thing has been taken as constant. So, in your maths book, you just try to find out the differential of cos hyperbolic x. So, next class you just tell me what is the expression for that, d dx of cos hyperbolic inverse x. You know that it will come up as some exponential function. So, if you differentiate it, you have to differentiate a E series. From that you will get. Now, in this simplified version, this has been taken as constant. So, that actually simplifies a lot of trouble. So, here how much we are getting? So, this T2 cancels out also H. So, dx by dA comes as so this is our expression. Now, we have to find out two things. You know this, what is from this equation, the first one I have given some number, no? The other equation that we are doing, no, this one I have given a number. So, this from this equation, what is the value of A? Now, you find one thing you should remember, that this offshore structure or barge, whatever you have taken, this actually oscillates about a mean position. So, this you remember, the moored barge oscillates about mean position. This is always the case. So that means what is this barge is doing, you will find out because of the variation in the external forces. You have assumed the external forces to be sinusoidal, so it will go in this direction, and it will come back, it will again drift in the reverse direction. So like this it is going to oscillate about this position, say let us position oscillates about A. So this is similar to your vibration studies, oscillates about A with a certain frequency, Then what is this X? What is this X? X is called static offset. X is known as static offset. Now in our expression you have to find out this small x, static offset, and what is the natural frequency of vibration. You have to calculate this from your equation. Natural frequency, so the motion that out here we are considering only one single motion. Say this is, we are analyzing, let us say surge. So you find natural frequency of surge. But you want to find out natural frequency, then you have to formulate your equation of motion. So this is called a static offset, vibrating about mean position A. So this is how the barge is behaving actually. So that means if you take normally in a spread mooring system, so this is say this is your offshore platform, say your semi-submersible or TLP for that matter, it will look like this. Say let us take a semi-submersible. TLP doesn't have a spread mooring system. So in your spread mooring system you will find the chain cables or anchor lines being attached at the four corners, say like this. Say this is the diagram of a semi-submersible. Semi-submersible on spread moorings. This is the equation. So on this now what you do, you just make an axis at the center, and you also draw another axis at the anchor point. So this is your local axis. So that means your cable tension is coming in this direction. This we will come back to this diagram later on, but what I want to say is coming back to your the behavior of the vessel. So that means what this is happening. Suppose you have anchored like the semi-submersible in this form. So if you take the CG of this semi-submersible, say at the center, say it will be located somewhere here. So this CG, it is once it is going in this direction, then it is going like this. So that means the vessel is actually going in this form, round like this, about this mean position A. So that is called vessel having percussion. About A. Vessel is having a percussive motion about A. It is going like this. The heave one I have not analyzed, but simply your surge and sway motions. Now the point that I want to tell you is that, so this is how the vessel is anchored at the four corners. Now suppose a storm comes. Now here actually you will find that the equations are not coupled. Whatever equations that we find out from the equation of motions, you will not get a coupled motion. That is, uncoupled motions are easy to solve. Suppose I snap one of these lines, anchor line snap. The tsunami has come, say it has actually happened in the Navy floating dock. This was a floating dock, and one of the anchor lines had snapped. So now you have to find out the forces, say without this, on the other lines. Calculate the maximum forces on the other lines. Now there you will have lot of coupling terms will come because the anchor lines are not symmetric. So you will find no coupling for symmetric anchor lines. Sorry. Now the job actually becomes more difficult for formulating your equation of motion, no coupling for symmetric anchor lines. Now you have to uncouple terms. Uncouple terms in equation of motion. And this is actually more complicated. In equation of motion, for unsymmetrical anchor lines. Vibration problem. This is one aspect of the case. Another aspect, you will find that whenever you are finding out the natural frequency of the surge, sway or whatever it is, better not to take damping terms. So neglect damping. I'll show you, I'll give you the equation of motion for a damped system. Neglect damping in equation of motion. Now some of these problems, since this is not a C-keeping class, those of you who are interested in solving this kind of equations of motions in surge, sway, heave, there is a chapter on C-keeping in Rossan and Tapa. There are some problems, you can work out the problems. So you neglect, if you want to simplify your equation of motion, this is the easiest job. Okay. Now the problem, if you have, will be more complicated if you have an anchor line snap. Now anchor line snap, actually this is your clients, they may require you to calculate with anchor line snap, because they want to check the reliability of the reliability of anchoring. So how many anchor line snaps the vessel can sustain. You will find once, because your environmental forces will be there, so you have to redistribute the environmental forces on the remaining lines, and you find out the maximum tension. Okay, so that is how the procedure that is normally followed with anchor line snap. So reliability of lines. So either they will tell you to calculate with one anchor line snap or two anchor line snaps, etc. Now of course there will be a limit to that. You cannot survive with simply one anchor line. Otherwise, then why you have given you so many anchors? It is quite expensive, isn't it? Not only that, if you are going for this kind of catenary anchor, so this distance can be as large as say 3 or 4 kilometers for semi-submersible, mode semi-submersible. Just one example. And here what I have shown you is only 4 lines, but actual practice you will find you have 3 in one corner. Say this represent, you will find out that you have to do this for normally when you calculate the anchor strength of the anchor lines, you calculate on the basis of, say, semi-submersible is moored at a particular location, isn't it? So extreme load conditions, or rather you write extreme 100-year storm condition. So normally in the reliability analysis that you have to do, see the mooring calculations are not as simple, because in the class you cannot go too much deep into this, because then it will take the whole semester. But in normally if you go into your your offshore companies, etc., they do, I think in Orcaflex you see if this option is there with one snap line. Okay, you can study this with one line snap, how much forces are coming, etc. So extreme 100-year storm condition, and normally the client will require you to make a matrix, sort of a matrix you have to give him with, say, 100-year storm condition, the maximum storm condition that is occurring. This you have to get from C spectra, again the previous class. So 100-year maximum wave. Next you have the 25-year storm criteria, 50-year storm. Like this you have to generate a matrix, okay, with say one anchor line snap, say two anchor line snaps. You do the calculation, say in Orcaflex with say 4 anchor lines, 6 anchor lines, 8 anchor lines, and all this. So you have to generate the design data, or a design matrix has to be generated with number of options. Whenever you are doing some mooring system design, you never give a client say with say 4 anchor lines. So he will ask you that you tell me what is the various configurations with various loading conditions. So your extreme storm conditions, now here actually what will come, you will find all these external forces are coming because of waves, wind and current. These are the normal forces are coming, of course, on floating platforms. So for all these spectra you have to calculate the maximum wave, wind and current forces, and these are actually summated for at all these points. If this is your point B, you find out all the forces that are coming at B, C, D and E. So the job is not all that easy, and we have to find out our matrix first with a number of, in the design situation. Design actually you will find, again you have coming again to a design spiral. The design situation you will find you generate matrix with different intensity of environmental forces. So that is why you require the help of a software. Intensity of environmental forces and different configurations of anchor lines. This client is going to ask you about this. The client is not going to be satisfied if you just giving a one-off answer. So normally in your ship design or a offshore structure, whether it is be for anchor lines or whether you go for pipeline or whatever it is, this he is going to ask for a set of design options. From that normally he selects. So ultimate criteria is your, in any offshore or shipbuilding, is a cost criteria. So there is always a trade-off. You will find there is always a trade-off between reliability and cost. There is always a trade-off. Now remember, in the offshore business, cost is a very, very important criteria, because this is a capital intensive venture. Thousands of crores are actually pumped into your seabed or your offshore platform. So who is going to foot the bill? So obviously there is always a trade-off between this reliability and cost. You want the system to be more reliable, then you have to pay for it. And if you want to less reliability, then it is okay, lesser amount of cost. So this is always the situation. Anyway, so that is why the reason is they ask for a design matrix, the client. So nowadays you have the softwares are all there, so it is easy to give these design options. So what I was talking about, we have found out the dx by dA term. Of course, we have made a simplification, and this is just one equation. Say we are trying to calculate this in surge, but similar equations you have to do for surge, sway, heave, pitch, and not only that, all these motions are going to come together. The ship will be having a surge, and also it will be having a say pitch, and at the same time it will be heaving. So that means there will be number of forces will be acting on the anchor line, which are superimposed one on another, are added, and then you find out the total force. So we will come to that, but this is the situation that is going to happen. So dx by dA we have found out. Now the point that we have to calculate is the cable stiffness. Now we have assumed that this A is equals to TH by W. So now you try to find out from this expression what is the value of dTH over dx. So this is what. Now your W is constant, so this is simple, W multiplied by dA over dx. Now this you can write as W multiplied by dx over dA to the power minus 1. Now your equation for x that we have got is, we have already found out dx by dx, so our problem is solved. So now you find out this dTH over dx. So that is equals to W multiplied by what? This expression. So minus 1 over 1 plus 2AH is to the power half plus cos hyperbolic is 1 plus HA. So this whole thing is to the power minus 1. So this is the analytical expression we have got for dTH by dx. Now we are going to use this expression. So this is called analytical method. Now where to use this expression? Now what is the value of TH? So TH you have to find out. There will be two terms for TH. One is a mean value. Next we have to formulate the equation for TH. TH, there is one mean value. You write this as M, and the other one is a variable term. So this you write as C11 eta 1. So let us say this 11 stands for the surge. Now this term C11 is called cable stiffness. Then what is eta 1? Eta 1 is called there is a term for this, is the horizontal offset. But this is, I think, at the CG. No, sorry. Horizontal displacement, you write. Horizontal displacement of point of attachment. Point of attachment of chain cable. With mood ship. Right? So find C11. Now if you want to find out C11, this THM is called the average horizontal force. Yeah, you have to make an assumption. So THM is average horizontal force. Now this, you write this as A equals to THM divided by W. So you will find in this expression there is a second term. Actually we have made this as constant, isn't it? This is the reason. This A we have found out as average horizontal force divided by W. This is why he has simplified this. So we have found out the C11. What is the value? C11 we have already found out. Now C11 cable stiffness, you write this as dTh over dx. So from this expression, what is the value of dTh? So dTh is equals to C11 multiplied by dx. Now that is what you have written in this expression. This eta 1 is the horizontal displacement and this is the mean value, this expression. So this is our expression for C11 then. So since C11 is equals to dTh over dx, so now you have found out cable stiffness, isn't it? So what is that expression? You have already found this out. So W multiplied by minus 1 over 1 plus 2a over h to the power half. So this is called the analytical expression for cable stiffness. And those of you who want to do it graphically, there is always a method. So this is called the analytical expression for cable stiffness. Now the other one is the graphical method. Now if you want to do the graphical method, you have to plot these values, TH and X. Now TH, we have found out the TH expression. You see, look into your expression of TH for the previous notes, you will find then you have to plot a graph like this. And x you can find out from, can you find out x? And th, what was the expression for th? So this you plot, vertical axis you plot th, and the horizontal axis you plot x, and you get a graph like this. This will be some kind of exponential curve. So th expression, what was the th expression? We have already derived one th expression. I think in last class I told you what was the expression for th. That expression t we have found out. Yeah. Now th you find out from t max. T max minus WH, that is the easiest expression. So from this you can find out TH, and X, how you can find out X? X you use that expression L minus LS, so these are two expressions you better use. So one is TH we can get from T max, and T max we have already derived as TH minus, this plus, and H is negative. So this expression we have already derived, and X you can find out from L minus LS. What is the other expression? Small x. But you have already derived small x expression, and LS expression you have already derived. Cx minus x naught, from that you can find out the expression for small x. Now you use these two equations and you plot your graph. Your graph will come something like this. Now you have to find out this value, and this value you find out at a particular location of TH. So that is why you find that A value we have used THM divided by W. So this is always, A is always found with respect to a particular value of TH. So you find out from here at one point, you calculate the tangent, you draw a tangent at this line, and then you find out this value of dth, and how much is this? This is your dx. Followed? So you find out this two values from the graph at a particular point of th. So th you can find out at, say, in our case you can find this at thm. Say this is your THM. So from this you can find out C11 is equals to dTH over dx. So this is from graph. So the analytical expression, you can find out the correctness of this because we have simplified the other term. So this you check by drawing a graph from the equations, from the cable line equations that we have got. So this, now but what we are going to do with this C11? So we have found out cable stiffness from what? Now there are three methods of calculation. One is called, first is the static analysis, then is the quasi-static, and the other one is the dynamic analysis. Now in this book, in the Fortinson book, the quasi-static he has not done. So first thing he has done this static analysis. Now from static analysis we are getting this value C11. Now this you have to put as input to your dynamic analysis program. So the dynamic analysis is the more important and crucial. So this you get an expression like your equation of motion. So this is your dynamic analysis. Now dynamic analysis in your vibration class, what you calculate? Dynamic analysis. Dynamic analysis, you you come across a factor which is called DLF. So this you calculate DLF. Anyway, the expression that I am going to give you now is a very complicated one. So say let us you find out equation of motion in surge. Say equation of motion will come out like this. Any equation of motion. Now there will be one mass term, that is your displacement of the ship, plus you have to find out another term which is called added mass. Say your surge motion, you write this as eta 1. So this is your inertia term. There will be other damping terms that will be coming out. So B11 is your damping. Now damping, actually there are two terms, one is the linear and the other is the non-linear term. So the linear damping is because of what? The linear damping is coming because of your chain cables. Damping, that is because of the structural damping that is come. Another term that is going to come and going to make the equation much more complicated is the hydrodynamic damping. So that is called BD. And hydrodynamic damping is the square of the velocity. So d eta 1 is your velocity. So this is dt multiplied by d eta 1. So this is similar to the drag term. This is called the hydrodynamic drag. And the other one is your cable stiffness, that is your stiffness force. So this is C11 eta 1. So this is equals to F1T. So this is your expression for one equation of motion. So you take only the surge equation. But this is your, these are the terms. So this is inertia. This you can write this as structural damping. This is hydrodynamic damping. Now what is this C11 eta? This is cable stiffness or spring stiffness. So this is why you will find that the anchor line is having a spring stiffness. Sometimes this is also called spring stiffness. And F1T is your external force. So you can see the equation of motion. You have studied vibration, now you apply this. Now you solve this equation. By solving this equation, what you will find? Equation of motion, once you solve, what you will get? You have to find out the dynamic displacement. There are two terms. Find dynamic displacement or what else? Natural frequency is very important. You find displacement and frequency. Displacement is nothing but amplitude. Now, why you are finding out the frequency? Compare omega with omega prime. So, this is coming from frequency of external force. Now, when this omega is equals to become equal to omega prime, then resonance will occur. So, now you have to avoid resonance of line. So, avoid resonance of cable, of chain cable in all conditions. In all conditions, remember this, your system should not have resonance with external force. And the natural frequency, what is the natural frequency from this equation? So, what was the long equation I had given? Can you find out a natural frequency from this? Vibration you have already done, no? Now, for your simplification, you just put B11 and BD equal to 0. Then what is the natural frequency? So, natural frequency is, say, omega that you have calculated is root over C11 over the added mass m plus A11. Of course, here you have not taken the damping term. So, remember we worked out what was our PD, damped frequency, root over p square minus n square, isn't it? So, this is what we have not found. We have rather simplified our equations. So, now you can find out this omega, or once you have calculated omega, you can compare with omega bar. You avoid resonance. Now, how are you going to avoid resonance? So, you avoid resonance either by changing C11 or m plus A11. Now, which one is the easiest? Easiest is the variation if you can vary this C11, because mass and added mass is very difficult to change. So, stiffness you change by, you change your cable tension. So, normally this is what we will come across in TLP also, the cable tension they change in order to avoid the resonance. Both you change resonance, the frequency, and also your percussion, excursion, that amplitude of vibration. So, both are equally important. Why? The reason is, this actually for our calculation you have taken this as 0. Now, the reason is, if you have this DLF large will be a problem, because this will lead to riser snap. Now, omega equals to omega bar will lead to chain cable snap. So, remember, these are the two very dangerous situations. The first one is pretty dangerous. The other one is, now the riser actually you have only one pipe. There are no this thing, other risers to take care of the load, but chain cable you have buffer, isn't it? That means the other chain cable can take the load. Riser snap is very dangerous. then you will have pollution, fire and all this will come. So anyway, with this we will end the discussion. Now after this I will just give you some of the equipments that are used